Hey, this is Leach with Simpson Math, and in this video, we'll be looking at a fundamental review of square roots. To get started, let's take a look at our perfect squares. So I've written out a list of just the first 10 perfect squares. There's obviously lots more. The perfect squares using integers, mind you. So 1 squared is 1, 2 squared is 4, 3 squared is 9, on and on up. You should have readily memorized especially the first 10, not maybe even through the first 15 or so, but you should be able to know, especially these numbers, these are the most common, these perfect squares. As you're working on square roots, it's not a bad idea to maybe have this written down if you don't have these memorized and internalized, because whenever I'm looking for my perfect squares to pull out, you need to be thinking of these numbers. Now, just to make sure we're clear, these numbers on the right-hand side are the perfect square. On the left-hand side, this is the math that produces said perfect squares, right? So if I was to square root, let's say 9, I end up with just 3. But if I was to square 3, I end up with 9, right? So to be clear, to go from this side to that side, we are squaring. To go from this side to that side, we are square rooting. Students get those terms mixed up, and I'll always try to correct you, kindly if possible, about these squares. So we square to make them bigger, typically. As long as it's a number bigger than 1, it'll get bigger. So we'll square to get it bigger. And then when we square root, to go in the other direction, right? So make sure we're clear about the square root versus squaring. All right, so let's take a look at the square root of 4. All right, now I have a video talking about exponents. And in that video, I talk about how 4 to the 1/2 power is the same thing as the square root of 4, where the index, there's an implied 2. So be mindful that if you see an exponent to the 1/2, that's a square root. So I have the square root of 4 is 2, right? So just from my list, if I see 4, what's the square root of 4? Well, it's the 2 without that square, because if I do 2 squared, I get the 4. If I square root the 4, I just get that 2 without the square. All right, so look for your perfect squares and then pull that out, because I can write this as 2 squared. Some people also think of kind of like the square root and that square reducing each other. In terms of exponents, they do, and then you'd be left with just 2 as another way of thinking about that. All right, so one more is that this 4 is 2 times 2. So sometimes people also think about pulling out a pair. So if a pair of 2s, those pair of 2s come out, and we're left with then that 2. They come out as one single one. All right, so let's take a look at this square root of 8. So what you need to do is you need to look for your perfect squares that are factors of that 8. Well, I can rewrite 8 to be 4 times 2. And 4 is a perfect square. Now, one thing with radicals is that we can say, if I have square root of AB, I can rewrite this as square root of A times square root of B. And it works in both directions. So since I have the square root of 4 times 2, an optional step, a step you don't have to show, is that this is square root of 4 times square root of 2. And then what is the square root of 4? Well, we just saw it a second ago, that it's just this 2. So find those perfect squares and square root it, and we're left with just 2 square root of 2. So 8 is 2 square root of 2. That is its exact value. Now, if you needed to approximate that, I know that the square root of 9 is 3, exactly. So 8 is a little bit less than that, so it's 2 point something, right? 2 point almost 9, so maybe 2.7, something about like that. All right, so for our next example, which you're going to do on your own, you're going to find, you're going to simplify square root of 32. And I actually have 2 different ways that I've worked to square root of 32. So find a perfect square that is a factor of 32 and pull it out. Make sure that whatever you have left over, if you end up with another perfect square left inside the square root, make sure to take that out as well. So pause the video and try this one on your own. All right, so welcome back. Here I have, I see that the largest perfect square, or one of the perfect squares within 32 is 16. 16 times 2 is 32. So I end up with, I can pull that 16 out as just 4, because square root of 16 is 4, and I'm left with 4 square root of 2. Now, if you were working this, you might have noticed that you could also do 4. Yeah, 4 works. Okay? So you can do 4 times 8, and that gets you 2 times square root of 8. But as we just saw up a second ago, is that 8 has another 4 in it, so I can break that apart into square root of 8 to be square root of 4 times square root of 2. So then we end up with the square root of 4 is 2. These 2's multiply, and we end up with 4. So it doesn't really matter which way you do it, but if you you can use any perfect square as long as it's a factor of that number, but it is fastest to use the largest. But if you don't find the largest, it's okay. So looking back at this work, if I was working this one, and for some reason I didn't come across the 16, I was like, oh, it's 4, and I see this 8. Always make sure to think, is there another perfect square? And now, since I found, I'll go, oh yeah, there's that 4 in there. What I might do, because I'm a perfectionist, I might kind of erase and backtrack. So if I know that there are 2 perfect squares inside of 32, I could just multiply those 2 perfect squares together. Those 4 times 4 is that 16. Now, at the end of the day, it doesn't really matter whether you find the largest one or not. Just find any of them. And then keep going. Just always evaluate what you have left. Is there another one left inside? If you don't find the largest one, it might take you a few times, or you can backtrack until you find it to help you get there. All right. Now, let's take a look at this common error. Some students will take the square root of a perfect square, but then leave the square root symbol behind. That is a very bad idea. Okay. So if I have square root of 16, okay, square root of 16 equals 4. Students will do this. They'll say square root of 16 equals square root of 4. No. And I often feel that they're just maybe in a hurry. But I have come across students that thought that that square root symbol stayed. It does not. And when you take the square root, it is gone. Just like if I said 4 squared, that equals 16. That does not equal 16 squared. If I left the square there, now that's a much bigger number than just 4 squared, right? So make sure once you use the square root to take the square root, that square root symbol goes away. All right, let's move on and let's take a look at square root of 38. All right, I want you to pause the video and try it on your own. Now, I was a little bit mischievous with this one because I wanted you to see that not every number has a perfect square in it. So the square root of 38, well, it's just square root of 38. Can't do anything else with it. Let me go through my thinking process for this. All right, so first, I think about square root of 38, and I think, okay, well, 38's even. That's good. So if you see an even number, there's a 50% chance. If I just see random even number, if I give you, here's a random even number, 50% chance that 4 is one of its factors. Now, in this case, it's not, but 50% chance that you could have. All right, so I try 4, and notice that if I'm showing this with skip counting, 4 goes into 32, 36, and 40, so it just skips over that 38. If 4 doesn't go into a number, 16 doesn't go in the number, so I really didn't even have to try 16. All right, so that's out the window. So let's try 9. All right, does 9 go into 38? No, it goes into 36, and then that's 2 away, so if I add, so the next 9 is 9 higher than 36, not just 2, it goes up to 45. So not 9 either, all right? And honestly, at that point, I'm done testing numbers. Here's why. The next perfect square is 25. The smallest multiplier that I could do here for typical finding square roots would be to multiply by 2. 25 times 2 is 50, bigger than 38. So because of that, I'm not going to find, there's not a perfect square. Sorry, because of that, I know that 25 is not, does not go into 38. Also, I know that 25s have to be multiples of 25. The zeros, 25, 50, 75, 100. They're really easy to find. It's not 38. So then that means that since 25 doesn't work, 25 is too big, I don't have to look at any of the others. Okay. Now, I've written down 36 and 49 just to show you. 36, again, is too big because if I times it by 2, 72. 49 is already too big, and I'm not multiplying by an integer to make it smaller. So 38 does not have a perfect square. That's sort of kind of the mental process. Again, if it's even, definitely try 4. If 4 doesn't work, 16 doesn't work, right? I really only have to try 9, which it doesn't work because once I hit 25, 25 is already too big because 25 times 2 is bigger than the 38. I'm done. I don't have to look anymore. I know for certain that there are no perfect squares in it. All right, so just to be clear, also, if you had to approximate that, what is that about? Well, I know that square root of 36 is 6. So square root of 38 is probably just guessing about 6.1, maybe 6.2. Well, it actually turns out that it's between those two. When I use my calculator, I approximated it to be 6.164, and that goes on forever. It never ends. It never repeats. It is irrational. Right? One last thing about square roots is this idea about rationalization. So if I see this 12 over square root of 3, 12 divided by square root of 3, that is not what we consider to be simplified. All right? So it's not fully simplified, so we have to fix this by method of rationalization. Now, just a note before we go into this. If you move on into higher mathematics, even within college algebra, pre-cal calculus, you'll see that there are some times that we might leave square roots in the denominator because simplification is just what is properly simplified. It's what's kind of prettiest. It's not a rule. Okay? It's not a rule that you have to follow. But it is, if you're being tasked to simplify, then yes, you need to, if you're tasked to fully simplify or to simplify, then you need to rationalize. Usually, you're always going to deal with this. But sometimes it gets way too gross, especially when you have variables and a bunch of stuff in it, that we might not mess with it sometimes in higher mathematics. But if it's just a straight number, you're going to be simplifying it. You're going to be rationalizing it. So let's take a look at how to deal with this. So that square root in the denominator, and it's really just a formality. It goes back when we were needing to divide things by hand, and it's also just a form of standardizing, so that way we know when things are common units and can be added or not. So we're going to rationalize. So to do this, I'm going to multiply by a fancy 1 again. We use fancy 1 quite a bit to be able to change things around. So I'm going to multiply by fancy 1. Now, why did I pick square root of 3 over square root of 3? So I'm going to multiply by something so that way my denominator no longer has a square root in it. Since I just have this single square root in the denominator, if I multiply square root of 3 times square root of 3 times itself, I'll be left with just 3. Because this is square root of 3 times square root of 3, which is square root of 3 squared, or square root of 9, which is then just 3. So I know that square root of 3 times square root of 3 is just 3. And then I multiply top times top, and I end up with 12 square root of 3. Now, I can reduce a little bit further. Just to be clear, this 3 and this 3, the 3 on the outside and the 3 in the square root do not reduce. Just like this 12 and this square root of 3, they do not reduce. When you multiply or divide numbers with square roots, you only do that. You do the insides together and then the outsides together. You cannot mix and match. Okay? So notice when I multiply these together, this 12 is on the outside, this 3 is on the inside. So I can multiply the outside, so 12 times 1, which is just 12. And there's kind of an implied square root of 1 attached to that 12, which isn't going to do anything with that square root of 3. So but I can reduce the 12 and the 3. 12 divided by 3 reduces to 4. All right, so let's take a look at this one. All right, if you're brave enough, pause the video and try this one on your own. Remember, I'm needing to rationalize, so the hint is I only am worried about that square root of 6. The square root of 5, that's fine. So pause the video, try this on your own. All right, so I'm needing to make this square root of 6 go away. So not go away, I'm needing the square root to no longer be a square root. This 5, it's fine. The math guys are not going to smite us for leaving this 5 down here. That's just a 5. It's this square root that's the problem. Also, again, about reductions. This 3, nope, don't even try that. You cannot reduce that 3 with that 6. This 5, nope, don't even try that. Can't reduce those. Only insides and outsides. If for some reason this was a, let's say, an 8 inside that square root, you could reduce if you wanted to. 8 over the 6 within the square root. Or if this was a 10 here, you could have reduced obviously with the numbers on the outside. Outsides together, insides together. All right, so now I'm going to multiply by fancy 1. Can't just multiply by square root of 6. Why is that okay? Because if I multiply by 1, it doesn't change the problem. Because we're using a different form of 1, so we call it fancy 1, we're just changing how it looks. So here, let's multiply. 3 times this 1 on the outside is just 3. Square root of 5 times square root of 6 is square root of 30. And then square root of 6 times square root of 6 is just 6. So then we're left with 30 in the denominator. Now, admittedly, you could reduce that 3 with that 6, be left with that 2 in the denominator at that step, but I chose to go ahead and move on. So that way, because I kind of want to, again, reiterate the fact, see this 30 and that 30? Don't even try it. This 30 is on the inside of the square root. This 30 is on the outside. They're not in the same area to be reduced. But you can reduce this 3 with that 30, and you'll be left with 1/10. So we have that 3 square root of 5 over 5 square root of 6 simplifies to square root of 30 over 10 when you properly simplify it by rationalizing. All right, so hope this video helped you understand square roots a little bit better. I'll see you in the next video. And remember, since math, we make math simple.